بسم الله الرحمن الرحيم. Vaporizers. Anesthetic vapor has to be diluted with fresh gas flow. So this is done by two things. First of all, by splitting. And this is what we call variable bypass vaporizers. And the second way is by injecting without split. This is called measured flow vaporizer. The first one, which is a variable bypass vaporizers, are divided into plenum vaporizers, and these are the vaporizer we already use in the theater, and the plenum vaporizer with electronic control as Aladdin, which we had mentioned before in the previous lectures. The second one is measured flow vaporizers, which is classified into this fluorine vaporizer, as we all know about it, and the direct injection of volatile anesthetic, as what we can see from this right side of the slide is the Macket injecting vaporizer. So this is the main classifications. Regarding the book I'm referring from is beginning with what we call the classification of vaporizers in the book is made on two types. We have what we call the plenum vaporizer. Plenum means you are blowing through, which we call it the positive pressure is being applied to the upstream, as you can see from the right of the slide, where the forcibly entered fresh gas flow goes through the vaporizer, creating the vapor pressure from the liquid, and then it comes out from the outstream system. Of course, this is a splitting type of vaporizer, or in another way, the draw-over vaporizer is that the patient is creating a negative pressure distal to the vaporizer to create the process of vaporization. Either he is being taking it spontaneously, or we can use an additional ventilator distal to this vaporizer. So this is the main classification regarding the book. The Boyle's bottle, which is a historical bottle, gives a hint about why did we make a new vaporizer. It is made of glass. Of course, glass is not as good as a conduction of heat as metals, copper, for instance. Of course, we are in need of heat to create the saturated vapor pressure, which is temperature dependent. So we can increase the surface area of this process of vaporization, but with what we call a cool. This cool is as the mock worn by the monks. You see, this makes the carrier gas going through the vaporizer close by the liquid anesthetic, causing bubbling. So we are trying to increase the concentration by, of course, the splitting ratio, which is controlled by a knob. Of course, this type of vaporizer, the drawback of it, that we cannot properly calibrate it. What's the meaning of that? That its concentration is being affected by different types of flow rates. So this is why we created the new types of vaporizers. So to overcome these problems in the design of vaporizer, we must assure, first of all, that the concentration coming out from the vaporizer is not much affected by the tidal ventilation entering to this vaporizer, whether it's low or high. As a beginning, we can see the normal vaporizer, which has an upstream and downstream with a control knob. For instance, we are using fluorescein. I'm talking about fluorescein, which is nearby to isoflurane. Both have similar, almost similar saturated vapor pressure, so we can consider both as similar. This bottle has a concentration of 32% from the pressure of it, which is around 32 kilopascal. So this pressure, in comparing to the 100, creates this concentration. So we have a very high concentration bottle. This is why we use it in a vaporizer. So how does the vaporizer work? Of course, we are controlling the concentration by the splitting ratio. Suppose 90% is bypassing the vaporizer and only 10% going through the vaporizer. So this will create a concentration of 3.2%. This is how we are controlling the concentration. So how can we make the concentration constant in respect of the flow by making the saturated or the vapor outcoming or emerging from the vaporizer is fully saturated? How can we make this? By two methods. First of all, we use wicks. As you can see, wicks are materials which be material or fabric. Half of it is being dipped in the liquid anesthetic ion by the surface area through the capillaries of this dipped material. The surface area is being increased much, and so we can increase the concentration. This is one of the methods. The second one is the centrete type. Centrete means that the fresh gas flow goes through a tube. This tube has holes. This holes, whenever the carrier gas comes out, creates bubbles. So these bubbles increase the surface area. So this is present in copper kettle. So these are the two types to increase the concentration of the anesthetic emerging from the vaporizer. The second thing regarding how we are constructing the vaporizer to overcome the problem of glass, as we said before, is constructing the vaporizer from a metal. So how can we calculate the heat capacity of the components of the vaporizer? For instance, we have a 5 kilogram weight of a vaporizer and 200 milliliter of halocene. Of course, we can figure out the heat capacity of halocene by multiplying the volume to the density of very important to memorize the density of halocene, which is 1.82 gram per each milliliter. It's very important so that we can figure out. Suppose we have a liquid in a gram weight, and we want to transfer it to a volume. So knowing the density, of course, definitely we can shift from a gram weight to a volume. So we are multiplying the volume to the density to create the figure plus the specific heat. So we will reach to this figure. Now if we want to apply it to the copper, of course, we can multiply the 5 kilograms times the specific heat of copper, which is strangely less than halocene, gaining a figure. These two figures are added to each other to increase the heat capacity of the vaporizer system to maintain a steady flow in respect of change of temperature. Of course, I am adding the water as a specific heat. Of course, we know that specific heat of water in case we are using water as a water jacket in the EMO vaporizer to maintain its temperature. The third thing as regarding the construction of vaporizer, what we call the thermal compensation. The thermal compensation, we want to assure that the anesthetic emerging from the vaporizer is constant in respect of any change of temperature. So we had three systems known. We have what we called the bimetallic strip. Bimetallic strip, as we can see from the lower part of the slide. I'm sorry, I don't have a pointer to show. We have three types to maintain this flow in respect of temperature. We have bimetallic strip. Bimetallic strip means two strips or one strip made of two metals of different coefficient of expansion. The two of them are joined together. Of course, whenever it's heated, one of them will be increase in length more than the other, which will take it with it to close the outlet of the vaporizer to decrease the amount of vaporizer emerging through it in hot atmosphere, and of course it contracts during cold atmosphere. So this is what we call bimetallic strip, and it's present in most of the thick vaporizer. The second is using a flexible pillows. This flexible pillows where we use mostly ether, which have a high specific heat. This, whenever it expands, it carries with it a rod. This rod controls, of course, the opening of the emergent of the anesthetic vapor from the vaporizer. And the third one is the metallic rod, which is present in Draeger type of vaporizer, which is made of two parts. This rod is expand during heat, closing the opening, minimizing the outcome from the vaporizer. Of course, to overcome this problem, we have what we call the semen vaporizer. The semen vaporizer, as we can see, has a throttle valve, and we, of course, we have an input and an output. This input through this throttle valve creates a different pressure. Of course, whenever the flow is high, the difference pressure will increase. So it will affect the final concentration, which is coming out from a small nozzle. This is a way to add droplets of liquid anesthetic or vapor to the circuit. So this difference in pressure across this throttle valve, which is affected by the flows entering, is adjusted so that it will continue to give the concentration constant in respect of this flow. This is controlled by the throttle valve, as we can see from the figure on the lower part. You see, this is the secret about the semen vaporizer to overcome this temperature compensation problem. Effect on pressure of vaporizer, or I didn't write here, which we can call it the pumping effect. What's the meaning of the pumping effect? Of course, whenever we use a vaporizer followed by an intermittent pulse pressure ventilation from a ventilator, and we are using a cross circuit with a low flow system, this may make back pressure on the vaporizer during the process of respiration. And whenever the process is being shifted to expiration, this release pressure will make the vapor coming out from two sides, from the downstream and upstream, both. So it will increase the concentration. This is why we are making different modalities to overcome this problem. First of all, the first one is to, of course, make a pressurized valve at the downstream to overcome the pressure, so it will not be affected by the pressure of the ventilation. The second thing is to making the a vaporizer chamber equal to the bypass chamber. What's the meaning of that? So that in case there is a back pressure, the amount of anesthetic emerging from the back part of the vaporizer through the upstream will occupy only the bypass, so it will not extend beyond this bypass, so that it will not increase the concentration. This is why we ought to have the concentration or the size of the vaporizer chamber equaling to the size of the bypass chamber. The third thing which is found in Draeger is making the inward tube from the upstream tortuous and long, so that when the back pressure increases, the vapor coming out through this pass, whenever the vapor comes out, it is by condensation will be transferred to liquid and return back to the vapor. So these are the methods to overcome the problem of the pumping effect. The meaning of decanted, we mentioned before that the spilling of the liquid anesthetic may, if in case of we are increasing the input of the liquid anesthetic inside the vaporizer, this too much increase may go through the system as a liquid, increasing the concentration. So of course we have the knobs to control this concentration to prevent this, what we call decantated into the breathing system. Use of the vaporizer in hyperbaric chambers. All of this contemporary vaporizer, the vaporizer we are used to, are not affected by either we go high with high pressure, or we go down, I'm sorry, we go up with low pressure, and we go down with as working in the hyperbaric chamber. It's not affected much by the pressure. What's the meaning of that? If, as we said before, if we have a vaporizer, this vaporizer is working as 100 kilopascal, and the concentration of hallucine in it, of course, whenever we know the concentration, we can figure out the by Dalton's law the pressure, which is 32 kilopascal. This 32 kilopascal is not affected by anything apart from temperature. So actually speaking, whenever I hit or held the knob at 1%, we are controlling the splitting ratio, assuring that what will come out is only 1%. This figure is being changed whenever I use a vaporizer in a high hyperbaric chamber where the pressure is 200. The figure which we had mentioned before, which is 32, will be 16, which means it's half of the one we mentioned before. This will create by the knob seated on one only 0.5%. But this 0.5%, though it's less, its density is high, and it has the same pressure, because as we said, the saturated pressure is not affected except by temperature. So this 1 kilopascal, whether from a normal atmospheric or double atmospheric, is important, because anesthetics work by the partial pressure of the brain. So you have a look on the figures downwards, where we have the two forms of vaporizer at different pressure, and we have the three methods to overcome the temperature compensation. And of course, we have the Siemens vaporizer, where the two side over the throttle valve, two pressure on the other over, it's been adjusted according to the flow by this throttle valve. Of course, we have a figure downward showing the a vaporizer inside the circuit, which is shown as we can see. It may be whenever I use a draw over vaporizer, it may affect the full concentration. Of course, the water vapor accumulating during the expiration will affect the process of concentration, and all these are the drawbacks of using draw over vaporizer. We have to have a special ventilator. We have to have a system to evaluate the concentration continuously, as we can see from the figure. Now we have some items regarding the control of the anesthetic machine with the vaporizer. Of course, the flush must be distal to the vaporizer, otherwise whenever we use it, we can create a high concentration. And the cutoff activated system, whenever the oxygen is cut off, must be distal to the vaporizer, so that the patient will not inhale a hypoxic measure. Of course, the vaporizer is being closed by a clockwise method, and we must assure whenever it's closed that there is no any anesthetic emerging from it, causing contamination. Of course, using vaporizer in tandem means that we are putting the vaporizer next to each other. Of course, whenever we suppose we don't have what we call the selectetic system nowadays, of course, you cannot use both of them at the same time. But in the past, the fluorescein can, if it's been put in the first line, can contaminate the second one and doing drawbacks. Draw over vaporizer, as we said, of course, this is a low system vaporizer system. We have the EMO, which is the Epstein-Macintosh exode. We had said before that has a water jacket for the latent heat of vaporization to be maintaining a steady temperature. We cannot use it for a continuous flow, and it's bulky, and it's used in remote hospital areas and in emergency. We have what we call the Oxford miniature vaporizer, which does not have a compensatory heat mechanism, and it can be used for continuous flow. And then we have a version from this Oxford, which is called the tri-surface vaporizer, which has the advantage of having an anti-freeze, so we can use it in very low climates, which will diminish the occurrence of freeze and which will affect the components of the vaporizers. Of course, as we can see, the filler tubes and the caps, which are used to minimize the mistake of putting different liquid and setting different vaporizer, and this is the saturated vapor pressure controlling or giving the relation between the temperature and the saturated and the vapor pressure of the anesthetic. Of course, whenever I increase the temperature, the vapor pressure increase till it reaches the boiling point. Of course, the boiling point of water, we know, is 100. Boiling point of this fluorine is nearly 23. That of isofluoryl halocene is around 50, and that of ether is around something and 30. See, so this is the importance of this first, and it can give me the concentration, and it gives me the vapor pressure of the anesthetic at any temperature. These are the figures of the Epstein-McIntosh figure. First of all, over the lower first to the left, and then we have the tri-surface system vaporizer, and we have the Oxford Benicia vaporizer, and then lastly we have the manual control. I forgot to tell you that in the past, to assure that the anesthetics is not affected much about the temperature, the vapor vaporizer in the early beginnings was controlled by a temperature, as you can see, and a knob. This knob contains two lines, a vertical and a transfer. These are intersecting with each other, giving the concentration. So I'm adjusting the concentration according to the temperature from this to give the correct concentration. This is, of course, was done manual before nowadays. Of course, it's automatic. And this is the copper kettle. I forgot to tell you the two things about copper kettle to control the thermal compensation. It has two flow tubes. One of them is bypassing, the other one goes to the vaporizer chamber by itself. This liquid vaporizer has a temperature, so I'm adjusting the temperature accordingly to the flow. So this is the method for thermal compensation, and making the flow not affecting the final concentration. So I forgot to tell you this through the talk of the lecture, which is the copper kettle, and this, of course, is this fluorine vaporizer, which almost boils at 23. This is why we have to have a electronic heated automated vaporizer, as we can see. Before it, I want to mention what we call the heated pulsed vaporizer. This is the beginning of the or the idea of the direct injection of liquid anesthetic to the circuit. The bottle is being attached to this system is made of a special tube. The tube has a solenoid valve. This solenoid valve opens rapidly in a special frequency, and has a heater in the upper part of it. With, of course, we have a heater, we have a thermostat, and we apply the bottle through it. It's the pressure of the bottle is 0.4 bar. So the liquid anesthetic is being vaporized by the heater, and then goes to rejoin the fresh gas flow. The point is that we are utilizing the fresh gas, the common gas law, which we can denote that it's made of PV equals nRT. So if we rearrange, we find the NV equals P over RT. So if we are assuring that the temperature is constant, we will find from this equation that we can adjust that the N on the V be constant, as long as the other side of the equation is constant. This assures that I know the number of moles to the volume given. This assures that I am giving the proper amount of moles according to the flow. So this is what we call the heated. It is heated pulsed vaporizer, pulsed because it is being transmitted through the solenoid valves. Now we come back to this fluorine vaporizer, as we said before. it is being put in what we call a sum. This sum is being heated to 39. Why do we heat it? So that it will not boil. It boils at 23. So whenever I exceed the boiling point of it, it will not boil. It will be kept as a liquid. So the vapor emerging from it is almost 2 atmosphere, to be adjusted by a pressure compensation to 1.2. This goes through pressure, differential pressure transducer. As we said before, the pressure is made of a diaphragm, which can correlate the pressure on the both sides of it. So one of the pressure of it in the upper part is coming from the fresh gas flow coming separately. Of course, this is not a splitting vaporizer, it is a measured vaporizer, because the flow is going through in another way, and the vaporization goes into another way, and they are joined. So this flow has a constrictor. According to the pressure difference between the both sides, which is transmitted by a processor to the system, I can adjust that constrictor so that the pressure across the differential pressure transducer to be constant, so that the amount of vapor coming from one side will tolerate the fresh gas flow in case of increase or decrease in flow, to assure that the concentration is constant. So this is the idea about the automated this flame vaporizer, which must be adjusted whenever I reach high pressure atmosphere or low pressure atmosphere. This is a hint. I hope that I succeed. Of course, you can find more and more of this subject in my site. Wassalamu alaikum wa rahmatullah wa barakatuh. Of course, vaporizer is considered as the bride of physics. In Quran, we consider Ar-Rahman is the bride of the Quran. You see. Wassalamu alaikum wa rahmatullah wa barakatuh.